Picture yourself floating in complete darkness, surrounded by nothing but the silent, infinite expanse of space. Your heart is pounding, your breath is steady but shallow inside your helmet, and your life depends entirely on the tool in your hand, a device that must function flawlessly on the very first try, because in orbit, there are no second chances. This isn't just a scenario from a science fiction movie. It's the daily reality for astronauts aboard the International Space Station, where a simple mistake could turn a routine repair into a life-threatening crisis. Here, in the absence of gravity, every action unfolds like a carefully choreographed dance between human intuition and the unforgiving laws of physics. Nothing is as straightforward as it seems. Even the act of turning a bolt or cutting a wire demands a level of precision and forethought that most of us never have to consider in our everyday lives. What few people realize is that behind these meticulously crafted instruments lies a hidden layer of psychological engineering, where every curve, texture, and mechanism is designed not just to function in zero gravity, but to work in harmony with the human mind under extreme stress. We often think of space technology in terms of thrusters, life support systems, and high-tech materials, but some of the most profound innovations are found in the tools astronauts rely on moment by moment. These aren't just pieces of hardware, they are masterpieces of empathy and insight, created to reduce cognitive load, prevent errors, and provide emotional reassurance in an environment where disorientation and anxiety are constant companions. From the gentle vibration that simulates the sensation of weight to the intuitive color coding that allows for instant recognition, these features are carefully crafted to keep astronauts focused, confident, and in control. In this video, we're going to uncover the fascinating psychology behind astronaut-tool-design, how NASA and other space agencies engineer not just for zero gravity, but for zero margin of error in human performance. We'll explore how something as simple as a wrench or a drill becomes a lifeline, shaped by principles of cognitive science, haptic feedback, and emotional design. And perhaps most surprisingly, we'll see how these innovations are already influencing the tools we use here on Earth, making everything from surgical instruments to consumer gadgets safer, more intuitive, and more responsive to our needs. So join us on this journey into the unseen world of space psychology, where every detail tells a story about what it means to be human in the most alien of environments. Back on Earth, gravity is the invisible force that makes our world predictable. It's the reason a tool placed on a workbench stays there until you pick it up again. It's what gives a hammer its satisfying impact and allows you to lean into a wrench for leverage. Our entire understanding of how to interact with objects is built upon this constant downward pull. But in the microgravity environment of space, every single one of these fundamental assumptions is turned upside down. The familiar rules of physics no longer apply, and ordinary tools become not just useless, but actively hazardous. Imagine the simple act of trying to turn a bolt with a standard ratchet. On Earth, you brace yourself, plant your feet, and use your body weight to counteract the torque you're applying. In orbit, that same action has completely different consequences. The force you exert doesn't just travel into the bolt, it also pushes your entire body in the opposite direction. Without gravity to anchor you, you would start spinning slowly, a phenomenon astronauts call the reaction force. A task that requires significant force could send you tumbling away from your workstation, turning a simple repair into a drifting emergency. This is why early space missions quickly discovered that terrestrial tools were a recipe for disaster. The dangers go beyond just spinning uncontrollably. Consider something as mundane as putting a tool down for a moment. On Earth, you release it and it stays put. In microgravity, that released tool doesn't fall, it floats. A screwdriver, a pair of pliers, or even a tiny screw becomes a floating projectile, drifting silently into sensitive equipment, potentially shorting out critical systems, or becoming lost in the labyrinth of a space station's modules. During the Gemini missions, astronauts reported the constant, frustrating challenge of tool chase, spending precious minutes hunting down floating instruments instead of working. This wasn't just an inconvenience, it was a massive waste of limited oxygen, power, and mission time. These challenges were starkly highlighted during the Skylab mission in the 1970s. Shortly after launch, a critical meteoroid shield ripped away, taking one of the station's two main solar arrays with it. The remaining array became jammed by a piece of debris. The entire mission and the lives of the first crew depended on astronauts performing an emergency spacewalk to free it. But NASA quickly realized the tools they had on board were utterly inadequate for the job. They had to rapidly design and build a pair of specialized 25-foot-long cable cutters, which the crew then used in a desperate and successful effort to save the station. This event was a terrifying wake-up call. It proved that a mission could be saved or lost not by the spacecraft's engines or computers, but by the design of a simple cutting tool. This realization sparked a revolution in thinking. Engineers could no longer just design for function. They had to design for the entire physical reality of the space environment. Tools needed to be tethered at all times to prevent them from floating away. Handles needed to be redesigned for gloved hands and for use by an astronaut who might be anchored by only 1 foot. The materials themselves had to be reconsidered. Producing metal shavings from a filing operation, for instance, would create a cloud of hazardous, floating conductive particles. Every single aspect of a tool's design, from its weight and balance to its method of operation, had to be reimagined from first principles. This fundamental rethinking of hardware for a gravity-free world set the essential stage for the next, even more sophisticated layer of innovation, designing these tools for the human mind operating under unimaginable pressure. Operating in the extreme environment of space means an astronaut's mind is constantly juggling multiple critical streams of information, monitoring life support systems, communicating with mission control, executing complex procedures, all while physically navigating a weightless, three-dimensional workspace. There is no room for a confusing or complicated tool to add to that immense mental burden. This is where the first and perhaps most vital psychological principle comes into play: cognitive load reduction. Every tool is meticulously engineered to be instantly recognizable, intuitively operable, and utterly unambiguous, stripping away any unnecessary mental steps between thought and action. Consider the simple act of selecting the right instrument from a tool bag. On a cluttered workbench on Earth, you might rummage around for a moment, but in space, with tools tethered and floating, that moment of hesitation or visual searching is costly. This is solved through a universal language of color. Handles are not a uniform gray, they are boldly colored with specific, mission-critical meanings. A red handle might indicate a tool reserved for emergency procedures only, ensuring it's never used accidentally for a routine task. A yellow handle could signify a high-torque tool, providing an immediate visual warning about the amount of force it will apply. This color coding system allows an astronaut's brain to bypass conscious analysis and move directly to pattern recognition, selecting the correct tool as quickly and effortlessly as we might distinguish a green traffic light from a red one. Beyond color, the physical form of each tool is sculpted for instant identification by touch alone. An astronaut, often with their vision partially obscured by a helmet or focused on a delicate task, must be able to reach into their kit and know exactly what they are holding. Wrenches have distinctly shaped grips that feel different from drivers. Cutters have a unique contour that separates them from pliers. This tactile differentiation is crucial. It means that in a high-pressure situation, perhaps during an emergency repair with limited time, an astronaut doesn't need to look down. Their hand tells them everything they need to know, freeing up their eyes and their conscious mind for the task itself. The pinnacle of this cognitive design philosophy is the pistol grip tool, or PGT, used extensively on the International Space Station. This is not a simple power drill. It's a computer-controlled torque-limiting device that looks like something from a sci-fi movie. Its brilliance lies in its deeply intuitive interface. It features a simple digital display and just a few buttons to control speed, direction, and torque. An astronaut can operate it entirely one-handed, a critical feature when their other hand is needed to stabilize themselves. But its most psychologically astute feature is the tactile and auditory feedback it provides. When a bolt is properly seated and the preset torque is reached, the tool doesn't just stop. It gives a distinct, satisfying click and a gentle shudder through the handle. This positive confirmation is felt, not just seen. In the noisy, visually chaotic environment of a spacewalk, an astronaut can be 100% certain a connection is secure without ever taking their eyes off their work. This sensory confirmation does more than just prevent errors. It builds a profound sense of confidence and control, directly reducing the anxiety that naturally accompanies a task where a single mistake could vent a spacecraft's atmosphere. By designing tools that feel like natural, predictable extensions of the body, engineers give astronauts one less thing to worry about, preserving their most precious resource in orbit, their focus. But what happens when even a perfectly designed, color-coded tool feels wrong in your hand? This brings us to the second, deeply fascinating psychological principle at play: the critical role of haptic feedback and the creation of an artificial sense of weight. Here on Earth, our bodies are in a constant, unconscious conversation with gravity. Our muscles automatically adjust to the heft of a hammer. Our nerves register the subtle vibrations traveling up a drill's handle. Our very sense of balance is tied to the pressure of our feet on the ground. In space, that entire sensory world vanishes. An astronaut's proprioceptive system, the internal map that tells your brain where your limbs are and what they're doing, is suddenly deprived of its most fundamental reference point. The result is a profound and deeply unsettling disorientation. In this weightless void, a tool that feels completely weightless doesn't just seem strange, it feels untrustworthy, almost alien. It provides no physical confirmation that work is being done. To bridge this sensory gap, engineers have become masters of tactile illusion. They design tools that actively lie to the astronaut's senses in the most helpful way possible, simulating the physical sensations of gravity and resistance that our nervous systems are hardwired to expect. This isn't just about making tools feel nicer. It's about providing essential feedback that prevents catastrophic errors. Consider the delicate task of tightening a bolt on a multi-billion-dollar satellite or a critical station component. On Earth, you can feel the increasing resistance in your wrist and shoulder. You get a physical sense of when you're approaching the limit. In microgravity, without that feedback, an astronaut could easily over-torque and strip a fastener, or worse, crack a crucial piece of hardware. Conversely, they might not apply enough force, leaving a connection dangerously loose. The solution is engineered into the tools themselves. The pistol grip tool we mentioned is a perfect example. It doesn't just stop electronically when it reaches its torque setting. It is designed to deliver a sharp, unmistakable jolt through the handle, a tactile click that the astronaut feels in their bones. This haptic signal cuts through the chaos of a spacewalk, providing an immediate and unambiguous confirmation of a job done correctly, a sensation far more reliable than trying to hear a click or see a tiny display readout while floating in a bulky suit. Other tools incorporate sophisticated vibration patterns. A low, steady hum might indicate the tool is operating normally, while a series of rapid pulses could signal a problem or that a specific phase of the operation is complete. These are not random vibrations, they are a carefully designed language of touch. Even the texture of a tool's grip plays a crucial psychological role. Surfaces are often slightly rough or patterned, not just for traction, but to provide constant, subtle stimulation to the nerves in the fingertips. This constant tactile input helps ground the astronaut, providing a small but important sensory anchor in an environment that offers very few. It's a reminder that they are holding something solid, something real, in a world where so much feels intangible. The psychological comfort this provides is immense. In a place where every sight and sound is foreign, the familiar sensation of a vibrating tool or a textured grip becomes a tiny piece of earth, a sensory touchstone that reduces anxiety and builds confidence. This artificial recreation of weight and resistance is perhaps one of the most empathetic aspects of space tool design, acknowledging that to function at their peak, humans don't just need tools that work, they need tools that feel right. This fundamental loss of a reliable up and down creates a constant low-level cognitive drain as the brain struggles to reorient itself, a condition that can lead to space adaptation syndrome, the technical term for space nausea. In this perpetually disorienting environment, a simple tool that requires a specific right-side-up orientation could become a source of immense frustration and even danger. If an astronaut has to spend precious seconds and mental energy just figuring out which way to hold a device, that's attention diverted from a critical task. This is why the third psychological principle of space tool design is so vital, embedding spatial orientation cues directly into the tools themselves to act as psychological anchors. Designers achieve this through a clever use of asymmetrical forms. Unlike a standard Earth-based screwdriver, which is typically symmetrical and can be grabbed any which way, many space tools are intentionally unbalanced in their design. They might feature an enlarged, contoured grip on one end that naturally fits the palm in a specific orientation, or a pronounced trigger guard that forces the hand into a particular position. This physical asymmetry means there is literally only one comfortable, correct way to hold the tool. An astronaut's hand, guided by ergonomics and muscle memory, automatically finds the right grip without the brain having to consciously process visual information to determine orientation. It becomes an intuitive, almost subconscious action, preserving mental bandwidth for the task itself. Beyond shape, visual markers play a crucial role in creating an artificial sense of direction. Tools are often adorned with highly visible arrows, stripes, or patterns that indicate the proper line of action or orientation relative to the astronaut's body. For instance, a series of green chevrons might point toward the business end of the tool, providing a constant visual reminder of the direction of force or operation. These aren't just passive markings, they create a visual language that helps an astronaut quickly establish a personal frame of reference. In the utter confusion of microgravity, where a crew member might be working with their head pointed toward what was formerly considered the floor. These markings on their tool become a fixed, trustworthy North Star. They allow the astronaut to define their own up and down in that moment, bringing order to the visual chaos. A perfect example of this principle in action is the Hubble space tape dispenser. On Earth, a tape dispenser is a simple, passive object. In space, it's a masterclass in oriented design. The dispenser used on the International Space Station is not a symmetrical box. It's a distinctively shaped tool with a large, pistol-like handle and a clearly defined top and bottom. It's designed to be operated with one hand, with the tape feeding out in a specific direction relative to the astronaut's grip. This intentional design means that during a repair, an astronaut can quickly grab the dispenser, know immediately how to orient it, and apply tape with precision without having to stop and think. This transforms the tool from a potential source of spatial confusion into a reliable partner that actively helps maintain situational awareness. The psychological impact of these design choices extends far beyond mere functionality. In an environment that constantly challenges an astronaut's most basic perceptions, a tool that feels familiar, predictable, and intuitively right provides a profound sense of stability. It becomes a fixed point in a spinning world, a small piece of controlled, understandable reality. This reduces the cognitive and emotional load of operating in such a hostile setting, allowing astronauts to feel more grounded and in command. By designing tools that combat spatial disorientation, engineers aren't just making tasks easier, they're providing essential psychological support, building confidence one intuitively oriented instrument at a time. In the high-stakes world of spacewalks and critical repairs, a simple mistake isn't just an inconvenience, it's a potential mission ender or worse. This is where the fourth psychological principle takes center stage: error prevention through affordance design. The term affordance might sound technical, but it describes something beautifully simple. It's the quality of an object that intuitively suggests how it should be used. A door handle begs to be pulled, a flat plate on a door begs to be pushed. In the gravity-free, high-pressure environment of space, affordance isn't just a design preference, it's a lifeline. Engineers meticulously craft tools to be physically impossible to use incorrectly, building psychological safety directly into their very form. This philosophy is brilliantly exemplified by the connectors used throughout spacecraft and on spacesuits. On Earth, plugging in a cord might be a simple affair, sometimes requiring a glance to align the shapes. In space, with limited visibility, gloved hands, and the ever-present risk of a mistake, that's not good enough. Connectors are designed with radical asymmetry. They feature unique patterns of pins and sockets, with subtle notches and guiding ramps that ensure they can only mate in one specific orientation. You can't force them together the wrong way, they simply won't fit. This physical impossibility eliminates a whole category of potential errors before an astronaut even has to think about it. The tool itself guides the action, making the correct move the only move available. Beyond connectors, safety interlocks are another masterstroke of affordance design. Consider the tools designed for handling orbital replacement units, the modular boxes that contain critical electronics on the International Space Station. These tools often feature a series of deliberate, sequential steps that must be completed before a component can be released or installed. A lever cannot be flipped until a safety pin is withdrawn. A handle cannot be turned until a locking mechanism is fully engaged. These aren't arbitrary complications, they are forced procedural checkpoints. They slow the operator down just enough to ensure every preparatory step has been completed, preventing a catastrophic premature release. The design of the tool literally enforces the correct procedure, acting as a physical checklist that an astronaut must interact with. Perhaps no mission better illustrates the life or death importance of this principle than the Hubble Space Telescope repair missions. Astronauts were tasked with performing incredibly delicate surgery on a priceless observatory, using tools that had to work perfectly on the very first attempt. There were no second chances, no opportunities to run back to the workshop for a different-sized wrench. Every tool was a custom-designed marvel of affordance. Screwdrivers were engineered to capture the fasteners they loosened, preventing any tiny screw from floating away and potentially shorting out Hubble's sensitive electronics. Power tools had multiple, redundant locking mechanisms to ensure they wouldn't accidentally disengage from a bolt. The design of each tool was a promise, a guarantee that if an astronaut could physically make the tool connect to the workpiece, they were doing it right. This eliminated the paralyzing doubt that could creep in during a billion-dollar repair job. The psychological impact of this fail-safe design cannot be overstated. For an astronaut suspended in the void, knowing that their tools have been designed to make failure almost impossible provides an immense sense of security and mental relief. It removes a tremendous burden of anxiety. They don't have to waste precious cognitive energy worrying about making a foolish error. The tool itself has their back. This allows them to channel their entire focus into the task itself, trusting that the instrument in their hand will guide them safely to success. This deep-seated trust between human and tool transforms a potentially terrifying procedure into a manageable, almost routine operation. It's the ultimate expression of empathetic engineering, understanding the psychological pressures of the user and designing a system that actively works to alleviate them. Yet for all their sterile, functional appearance, these instruments often become far more than mere devices to the astronauts who rely on them. They transform into trusted partners, silent companions on an unimaginable journey, and even develop a kind of personality. This emotional connection forms the fifth, and perhaps most human, psychological principle of space tool design: the deliberate fostering of personal bonds between astronaut and instrument. In the profound isolation of space, where every object is a piece of engineered hardware, a tool that feels uniquely yours provides a psychological anchor that is as vital as any physical tether. Designers intentionally cultivate this bond through elements that invite personalization and tactile familiarity. While every tool must meet rigorous safety and performance standards, there is often room for subtle customization. The texture of a grip, for instance, is not chosen solely for its non-slip properties. Some astronauts might prefer a more aggressive, knurled pattern that provides maximum feedback through their gloves, while others might favor a slightly smoother, contoured surface that fits their hand like a well-worn baseball. These choices are not arbitrary. They are offered to allow the astronaut to select the tool that feels most intuitive and comfortable to them personally. This sense of choice, of having a say in the instrument you will bet your life on, is powerfully affirming. It transforms the tool from a piece of issued equipment into a personal selection, a part of their individual kit. Beyond selection, the tools themselves are often designed to be adjustable. Handles might feature interchangeable palm rests or adjustable finger grooves that can be tuned to the astronaut's specific hand size and strength. This level of customization does more than improve ergonomics. It sends a powerful psychological message: this was made for you. In an environment where so much is standardized and non-negotiable, the ability to make a tool fit your own body is a small but significant act of autonomy. It reinforces the astronaut's sense of agency and control at a time when they are largely at the mercy of complex systems and mission protocols. The tool becomes an extension of their will, a physical manifestation of their capability. There are even subtle aesthetic touches that, while never compromising function, add a layer of personal identity. A mission patch might be laser etched onto a non-critical surface, or a serial number might be displayed in a distinctive font. These tiny details are the equivalent of a name engraved on a favorite pen or a sticker on a laptop. They don't change how the object works, but they change how we feel about it. They make it ours. For an astronaut on a months-long mission, seeing their mission insignia on a tool they use daily is a constant, quiet reminder of their purpose and their team, a small flag planted in the impersonal landscape of their metallic world. The psychological benefit of this connection is profound, especially during long-duration missions marked by isolation and immense pressure. A complex, hours-long repair task is not just a technical challenge, it's a mental marathon. Having a tool that feels familiar, reliable, and personally suited to you can dramatically reduce the cognitive and emotional fatigue of the work. It eliminates the small, nagging frustrations of an awkward grip or an uncomfortable hold, allowing the astronaut to enter a state of flow where the tool feels like a seamless extension of their own body. This deep familiarity breeds a quiet confidence, a certainty that they can trust their hands to know what to do even when their mind is tired. In the silent, airless void of a spacewalk, that trust is everything. It turns a potentially lonely and terrifying experience into a focused, almost meditative collaboration between human and machine. This emotional dimension reveals the true depth of space tool design, showing that it addresses not just the mechanical needs of the task, but the whole human experience, the need for comfort, for familiarity, and for a sense of personal connection millions of miles from home. This journey into the psychology of space tools didn't happen overnight. It's a story of gradual, hard-won evolution, a century of accumulated wisdom written in the handles and mechanisms of the instruments themselves. If we look back across the decades of spaceflight, we can see a clear arc, a progression from treating tools as simple mechanical objects to understanding them as vital interfaces for the human mind under stress. The Mercury program, America's first manned venture into space, was fundamentally about proving humans could survive the journey. The toolkits reflected this bare-bones philosophy. For Alan Shepard's first suborbital flight in 1961, the entire tool complement was arguably just the spacecraft's controls themselves. The mission was so short and the capsule so cramped that there was no concept of repair or external work. The psychology at play was one of pure survival, not performance. It was the Gemini program that first forced the issue. With longer missions and the ambitious goal of spacewalks, NASA had to confront the reality of humans needing to do things outside the spacecraft. The tools for these early extravehicular activities, or EVAS, were almost comically crude by today's standards. Astronaut Ed White's historic first American spacewalk used a simple handheld gas gun for propulsion, a device with minimal controls and no feedback. The tools were basic, off-the-shelf items modified with tethers. They were engineering solutions to mechanical problems, with little consideration for the cognitive load or spatial disorientation the astronaut would experience. The famous tool chase problems, where astronauts would fumble and watch their equipment drift away, were not just embarrassments, they were the first crucial data points. They proved that a tool that works perfectly on an Earth-bound bench could be utterly useless, even dangerous, in space. The psychological lesson was stark. The environment changes everything about human performance. This set the stage for the Apollo era, where the stakes were unimaginably high and the missions infinitely more complex. Apollo astronauts wouldn't just be floating outside a capsule. They would be walking on another world, conducting scientific work, and living in a lunar module. For the first time, psychology became a deliberate, though still emerging, part of the design process. The tools for the lunar surface, like the scoops, rakes, and sample tongs, were designed with the moon's 1/6 gravity and the astronaut's bulky, pressurized suit as the primary constraints. But engineers also began to think about the user's mental state. Color coding was introduced on tool handles for easier identification against the gray lunar soil. Tools were designed to be used with one hand, acknowledging that an astronaut might need the other to stabilize themselves on the uneven surface. The iconic image of the lunar module pilot's checklist, securely mounted on his wrist, is a perfect example of early cognitive load reduction, putting vital information directly in the line of sight to prevent potentially fatal mistakes. Apollo was the transition point where tools stopped being just hardware and started becoming partners in the mission. The Space Shuttle program marked the true professionalization of spaceflight, and with it, a giant leap in psychological integration. The shuttle was a workhorse, a flying laboratory, and a repair truck, and its crews included mission specialists who were not just pilots, but scientists and engineers. The tools had to support a huge variety of tasks, from satellite deployment to complex repairs. This is when we see the birth of truly cognitive tools. The pistol grip tool, with its digital readouts and torque settings, is a product of this era. It didn't just apply force, it processed information. It was designed to prevent human error by ensuring a bolt was tightened to a precise specification every single time. The entire concept of the MMU, the Manned Maneuvering Unit, was a psychological marvel. It transformed an astronaut from a passive passenger on a tether into a free-flying pilot, a shift that required entirely new intuitive controls and spatial awareness cues. The shuttle era's lasting psychological contribution was the principle of cognitive efficiency, streamlining the interaction between human and tool to save time, prevent error, and reduce mental fatigue during missions that could last weeks. This evolutionary path culminates in the International Space Station, a permanent human outpost that represents the most holistic application of psychological principles to date. With international crews living and working in space for 6 months or more, tool design has expanded to encompass not just performance, but well-being. The design philosophy is now human-centered in the fullest sense. Tools are stored in meticulously organized packs, with each item having a specific, familiar place to reduce the cognitive load of searching. Handles are ergonomically sculpted not just for a gloved hand, but for prolonged use, reducing physical fatigue that leads to mental fatigue. The materials are chosen for their visual and tactile pleasantness over time, not just their function. Every aspect, from the sound a tool makes when it's used to the way it feels when it's stowed, is considered for its long-term psychological impact on the crew. The ISS is the living library of all these accumulated lessons from Mercury, Gemini, Apollo, and the shuttle. It demonstrates how far we've come, from hoping a tool would work, to knowing it will work, to designing it so it actively cares for the mind of the person using it. Perhaps no mission better illustrates the profound marriage of psychology and engineering than the Apollo lunar landings. Stepping onto the moon was more than a physical journey. It was an unprecedented psychological experiment. The astronauts faced a world with 1/6 of Earth's gravity, encased in pressurized suits that turned their own bodies into stiff, cumbersome machines. Their gloves, essential for survival, were a nightmare for dexterity, inflated like balloons, reducing tactile sensation to almost nothing. Every tool they used had to overcome these brutal physical constraints while simultaneously supporting their mental state, keeping them focused and confident during humanity's first footsteps on another world. The tools of Apollo weren't just instruments, They were psychological lifelines designed for an environment where a simple dropped hammer could mean a lost scientific opportunity, or worse. Consider the challenge of tactile feedback. An astronaut wearing those thick, multi-layer gloves couldn't feel the subtle vibrations of a tool or the texture of a rock. Their sense of touch was muffled, like trying to thread a needle while wearing winter mittens. Tool designers had to compensate for this sensory deprivation by amplifying feedback through other means. The lunar hammer, for instance, wasn't a standard claw hammer. It featured a long, lightweight handle made of aluminum tubing to keep overall weight down, but its head was made of heavy, solid chromium-plated steel. This unique balance was a psychological masterstroke. The heavy head created significant inertia when swung. Even through the stiff glove, the astronaut would feel a pronounced thump travel up the handle upon impact, a clear, unmistakable confirmation that they had struck their target. This engineered sensation replaced the lost feeling in their fingertips, providing the crucial feedback their brains needed to understand the consequences of their actions. Without it, they might have been swinging blindly, unsure if they were even making contact. This principle of amplified feedback extended to the sampling tools. The lunar scoop and tongs were designed not just to collect material, but to communicate their success. The scoop had a sharp, serrated edge that required the astronaut to put their body weight into it to bite into the lunar soil, or regolith. This physical effort leaning into the tool provided a clear kinesthetic signal that work was being done. The tongs were spring-loaded, designed to be squeezed with the entire hand rather than delicate fingers. When they clamped down on a rock, the spring pressure would fight back against the glove, creating a resistance that the astronaut could feel in their wrist and forearm. This resistance was the tool's way of saying, "I have it." In an environment where their hands were nearly useless, these tools became prosthetic senses, translating the alien world into physical sensations the astronauts could understand and trust. Visual communication was equally critical. Inside the helmet, an astronaut's field of view was restricted, and looking down at their tool belt required a deliberate effort. To solve this, the Apollo toolkit became a rainbow of color-coded identifiers. Handles were painted in bold, high-contrast colors: orange, yellow, blue, and black. A quick glance was all it took to distinguish the rock hammer from the scoop or the extension handle from the sampling bag. This system drastically reduced cognitive load. During the intense, time-pressured moonwalks, an astronaut couldn't afford to waste precious seconds fumbling through identical-looking tools. The color coding created an instant visual language, allowing for rapid, error-free selection. It was a simple solution with a profound psychological impact. It eliminated a source of potential frustration and delay, keeping the astronaut in a state of flow and focused on their scientific objectives rather than on their equipment. Perhaps the most psychologically astute design element was how the tools leveraged the lunar gravity itself. On Earth, a hammer's weight is in its head, and the force of a swing comes from the user's arm and the pull of gravity. On the Moon, that gravity is mostly gone. Apollo tools were carefully balanced to work with the Moon's gentle pull, not against it. The hammer's long, lightweight handle allowed for a wide, sweeping swing that used the astronaut's body momentum to generate force, with the heavy head doing the rest. This meant the tool felt natural and intuitive to use. It behaved in a way that matched the astronaut's Earth-born expectations, even in a fractional gravity environment. This familiarity was a psychological comfort. In a landscape of overwhelming strangeness, using a tool that felt predictable and responsive provided a tiny island of normalcy. It built confidence, assuring the astronauts that they were in control and capable of performing their work effectively. The ultimate proof of this psychological success is found not in technical manuals, but in the astronauts' own words and actions. Film from the lunar surface shows them working with a quiet competence, their movements assured and deliberate. They didn't struggle with their tools, they used them as the natural extensions of their bodies they were designed to be. In post-mission debriefs, they reported feeling surprisingly comfortable and capable with the equipment, a testament to the countless hours of human factors engineering that went into every curve and contour. The tools performed flawlessly, yes, but more importantly, they made the astronauts feel flawless. They transformed what could have been a clunky, frustrating struggle into a graceful ballet of human exploration. The psychological security built into those aluminum and steel instruments played a silent, crucial role in the success of Apollo, proving that when you design for the human mind, you empower the human spirit to achieve the extraordinary. Inside the cramped modules of a spacecraft or space station, every inch is precious real estate, and every movement must be calculated. This extreme spatial constraint presents a monumental challenge for tool design, one that goes far beyond simple miniaturization. It demands a deep understanding of anthropometrics, the scientific study of the measurements and capabilities of the human body. Designing for space isn't about creating the smallest tool possible. It's about creating the most efficient tool for a human operator whose own form is dramatically altered by a bulky, pressurized suit, all within a workspace that offers virtually no room to maneuver. A tool that is perfectly designed for a bare hand on an open workbench on Earth becomes a clumsy, frustrating, and even dangerous object when used by a fully suited astronaut in a narrow passageway. The pressurized glove is perhaps the single greatest obstacle to dexterity and the primary focus of anthropometric design. Imagine trying to perform a delicate task while wearing a pair of stiff, inflated winter mittens. Your fingers can't spread apart easily, your sense of touch is muffled, and your hand is locked into a semi-curved position. A standard tool handle designed for the wide grip span and sensitive fingertips of a bare hand is completely unusable. This is why space tool handles are significantly larger in diameter. They aren't just thicker, they are engineered to fill the void inside the glove, providing a secure and stable purchase for a hand that can't precisely feel what it's holding. The surface is often contoured with pronounced grooves or ridges. These aren't for aesthetic appeal, they act as physical guides, locking the glove's fingers into a specific, optimal position to prevent the tool from twisting or slipping during use. The handle's shape essentially does the gripping for the astronaut, compensating for the glove's inherent clumsiness. The angle at which a tool meets the work surface is another critical factor dictated by anthropometrics. On Earth, we constantly adjust our body position to get the best leverage on a task. We lean over, kneel down, or shift our weight. In the cramped quarters of a spacecraft, those adjustments are often impossible. An astronaut might be anchored in place by a foot restraint, their mobility severely limited. A traditional right-angle power drill, for instance, would require them to position their entire body at a specific orientation to the workpiece, a luxury they rarely have. This is why many space tools, like the pistol grip tool, feature a straight line or inline design. The force is applied directly along the axis of the astronaut's arm, allowing them to engage a bolt or fastener from a much wider range of body positions. The tool's operational range, the physical space needed to use it effectively, is dramatically reduced, turning a task that might have been impossible in a tight corner into a manageable one. The psychological impact of this anthropometric precision is profound and often overlooked. Physical strain directly translates to mental strain. When an astronaut has to fight with a tool constantly re-gripping a slippery handle, contorting their wrist into a painful angle to reach a bolt, or expending excess energy to maintain control. It creates a steady drain on their cognitive resources. This is mental bandwidth that should be dedicated to the complex procedure itself, to monitoring their oxygen levels, or to communicating with mission control. Instead, it's wasted on battling poor ergonomics. Conversely, a tool that feels like a natural extension of their gloved hand is psychologically liberating. It creates a sense of effortless control and mastery. The astronaut isn't thinking about the tool, they are thinking about the task. This seamless integration reduces frustration, builds confidence, and allows them to maintain focus and clarity during hours of demanding, high-stakes work. In an environment where a single moment of distraction can have catastrophic consequences, a perfectly fitted handle is not a luxury. It is a critical piece of psychological life support. Beyond the shape and function of a tool lies a deeper, more sensory layer of design that speaks directly to the human psyche, the very materials from which it is made. In the sterile, metallic world of a spacecraft, the substance of a tool is not chosen solely for its strength-to-weight ratio or its thermal properties. Every material carries a psychological weight, a silent message that can either soothe or strain an astronaut's mind over the long months of a mission. The cool, substantial feel of a titanium housing isn't just about durability. It conveys a sense of permanence and reliability. The smooth, matte finish of anodized aluminum isn't merely corrosion-resistant. It presents a visual cleanliness that feels orderly and controlled. These choices are a form of nonverbal communication, telling the user that this instrument is trustworthy, professional, and built for the severity of the environment. This psychological impact is most apparent in the battle against visual fatigue. The interior of a space station is a labyrinth of gleaming metal surfaces, brightly lit monitors, and countless reflective components. Adding a highly polished, mirror-like tool to this environment would be a recipe for eye strain and distraction. Glare from a chrome-plated surface could momentarily blind an astronaut during a critical procedure or create confusing reflections that disrupt their spatial awareness. This is why non-reflective, matte finishes are the universal standard. These surfaces absorb light rather than throwing it back, creating visual calm amidst the technological chaos. They allow the astronaut's eyes to focus effortlessly on the task at hand, reducing cognitive load and preventing the headaches and irritation that can come from constant squinting and visual adjustment. The material's finish, therefore, isn't just a coating. It's a carefully considered feature that protects the user's mental comfort and focus. The sense of touch is equally catered to through deliberate texturing. A smooth, polished metal handle might look sleek, but in the grip of a pressurized glove, it could feel slippery and insecure. That subtle anxiety of a tool potentially twisting loose at a crucial moment is a psychological burden astronauts should never have to carry. To prevent this, surfaces are engineered for positive grip. Handles might be coated in a textured polymer that provides high friction, or the metal itself might be etched with a precise pattern of grooves that bite into the glove's material. This isn't just about physics, it's about psychology. The constant, subtle feedback of a secure grip provides a subconscious reassurance that builds confidence with every use. The tool feels locked in, solid, and dependable. This tactile certainty allows the astronaut to apply their full attention to the procedure itself, rather than wasting mental energy on micromanaging their grip. Even color, as a property of material, is selected with a dual purpose. The bold yellows, reds, and blues we see on tool handles are, of course, for instant visual identification. But these hues are also chosen for their psychological effect. Softer, cooler tones like blue might be used on frequently handled tools to promote a sense of calm during repetitive tasks. Warning red is reserved for critical or emergency equipment, leveraging a universal psychological cue for caution and importance. The specific shades are often muted rather than neon bright, avoiding a visual jarringness that could become grating over time. The color palette of a tool kit is designed to be functionally clear yet psychologically harmonious, contributing to a work environment that feels organized and intentionally designed, not chaotic and overwhelming. Perhaps the most sophisticated psychological trick involves engineering a tool's sound. In the vacuum of space, there is no air to carry sound, so outside the station, a spacewalk is conducted in eerie silence. Inside, however, the acoustic environment is a constant hum of machinery. In both cases, the sounds a tool makes are a critical source of feedback. Designers select and pair materials to create specific auditory signatures. The engagement of a titanium gear inside a housing might be designed to produce a distinct, satisfying click that is clearly audible over the background noise. The sound of a ratchet mechanism needs to be sharp and definitive, signaling each successful increment of torque. These sounds are not byproducts, they are features. They provide an additional sensory channel for confirmation, allowing an astronaut to hear that an operation is proceeding correctly without having to constantly visually verify a readout. This multisensory design, combining touch, sight, and sound, creates a rich tapestry of feedback that keeps the user fully informed and situationally aware. It demonstrates that every physical property of a material is seen not just as an engineering parameter, but as a potential channel for psychological support, ensuring the astronaut feels connected, confident, and in control through every sense available. In the void of space, the concept of a spare part takes on a weight far beyond its physical mass. It's not merely an insurance policy, it's a psychological anchor. For every mission-critical tool, there exists at least one, sometimes several, identical backups. But the philosophy behind this redundancy is far more sophisticated than simply having a second copy. The design of these backup systems is a masterclass in psychological engineering, aimed squarely at one goal: eliminating the gut-wrenching fear of failure from an astronaut's mind. A spare tool that is confusing, hard to access, or subtly different from the primary can be worse than no backup at all, seeding doubt and hesitation when every second counts. True psychological security is engineered through a principle of perfect familiarity paired with deliberate, clear differentiation. This delicate balance is most visible in the system of color coding. The primary tool an astronaut trains with for months on Earth, the one that becomes an extension of their muscle memory, always has a specific color scheme, perhaps a black handle with a green stripe. Its immediate backup, however, might feature the same black handle but with a bright orange stripe. The form, the weight, the feel in the hand, all of it is identical. The only difference is a high-visibility visual marker. This design ensures that in a high-stress moment, an astronaut's hand doesn't hesitate. The motor memory is the same. They don't have to learn a new grip or adjust their technique. Their brain can immediately trust that the backup will perform exactly as the primary would, because in every meaningful way, it is the same tool. The color change isn't a warning. It's a simple, clear identification that says, "I am your spare, but I work just as well." This prevents the subtle, subconscious anxiety that might come from grabbing a tool that looks completely foreign. A design that could introduce a microsecond of doubt in a situation where confidence is everything. Where and how these backups are stored is equally critical to the psychology of security. they are never buried at the bottom of a generic storage locker. Their placement is a matter of rigorous protocol. A backup for a tool used on the station's exterior during a spacewalk will be mounted in a specific, easily accessible location on the cruise suit or on a workstation, often within the astronaut's direct line of sight. The act of deployment is also engineered for simplicity. A backup tool might be secured with a single, large Velcro strap that can be ripped away with a gloved hand, or it might sit in a custom-shaped cradle that allows it to be grabbed in one smooth motion. The goal is to make the transition from primary to backup as seamless and thoughtless as possible. There are no complex latches to fumble with, no boxes to open. This reduces the time-to-task resumption, which is a technical way of saying it gets the astronaut back to solving the problem instead of wrestling with their equipment. This flawless accessibility is a silent promise. If your main tool fails, your recovery will be swift, simple, and certain. You will not be left stranded. The ultimate psychological benefit of this system is the freedom it grants, knowing on a deep, unquestionable level that a proven, familiar, and instantly available backup is right there allows astronauts to operate with a degree of calculated boldness that would otherwise be unthinkable. It transforms a potential crisis into a manageable hiccup. This security blanket of redundancy empowers mission planners and astronauts alike to attempt complex, ambitious repairs and procedures that push the boundaries of exploration. The anxiety of a catastrophic mission-ending equipment failure is lifted. Instead of a paralyzing what-if scenario, a tool failure becomes a simple what's next procedure. Grab the orange striped version and continue. This psychological shift is profound. It changes the emotional landscape of a spacewalk from one of high-risk peril to one of confident, capable problem-solving. The tools are not just designed for their primary function, they are designed to support the human spirit, ensuring that courage is never undermined by the fear of being left without a plan B. This deeply embedded sense of security is what enables astronauts to turn their attention away from their equipment and fully toward the wonders and challenges that lie before them. This incredible focus on the individual user, however, had to evolve once again when humanity's outpost in space became a truly global village. The International Space Station is not an American or Russian project. It is a masterpiece of international cooperation, built and operated by space agencies from the United States, Russia, Japan, Europe, and Canada. Suddenly, the user base for every tool expanded to include astronauts from vastly different cultural and engineering backgrounds. A design that felt perfectly intuitive to an American engineer might be completely baffling to a Japanese astronaut, and vice versa. This presented a new frontier in psychological design, creating tools that are not just human-centered, but culture-blind, speaking a universal language of function that transcends borders and native tongues. The first challenge was the most basic: symbols and colors. On Earth, a simple arrow seems universally understood, but even its meaning can be culturally dependent. Does it indicate direction of movement or direction of force? A green light might universally mean go, but the specific shade and context matter. Tool designers had to abandon any assumption of cultural knowledge. They turned to ISO standards, the International Organization for Standardization, which provides a library of symbols that have been tested for cross-cultural recognition. A wrench symbol means tighten or loosen to anyone, anywhere. A lightning bolt inside a circle means electrical hazard. These symbols become the first layer of a common visual language, replacing written instructions that would require translation and could be misread in a high-stress moment. Color, too, was standardized with extreme care. The red used for emergency releases or critical warnings is chosen to be distinct from other reds used in different contexts onboard, ensuring that its urgent message is immediately and unambiguously understood, regardless of the viewer's cultural background. This philosophy extends to the very operational logic of the tools. Consider something as simple as a knob. In many Western cultures, turning a knob clockwise means on or increase, while counterclockwise means off or decrease. But this is a learned convention, not a universal truth. For a tool that must be operable by anyone in an emergency, relying on this assumption could be disastrous. The solution is to design out the ambiguity. Instead of a smooth knob, engineers might use a lever that has clear, physically detented positions marked with those universal ISO symbols, a plus sign for increase, a minus for decrease. The tool itself guides the hand to the correct action, making the intended use physically obvious. This approach eliminates the need for cultural memory. The design enforces the correct procedure through its physical form. It's a perfect example of affordance design scaled to an international level. The process of achieving this clarity is itself a lesson in intercultural collaboration. The design of a major station tool is never done in isolation by one nation's engineers. It undergoes a rigorous review process with all international partners. A prototype developed by NASA will be sent to JAXA in Japan and Roscosmos in Russia, where their human factors experts and astronauts will put it through its paces. This is where subtle but critical differences emerge. An American astronaut might prefer a larger, more assertive trigger on a power tool, while a Japanese astronaut might find a smaller, more delicate switch to be preferable for precise control. The final design isn't a compromise that satisfies no one. It's an optimized solution that incorporates the best insights from all perspectives. The handle might be contoured to accommodate a wider range of hand sizes, or the control interface might be simplified to its most essential elements to avoid any cultural preference for complexity or simplicity. This collaborative design process does more than just create a better tool. It builds a shared psychological understanding and mutual respect among the international teams, forging a common culture of safety and efficiency in orbit. The psychological impact of this successfully universal design is a powerful sense of inclusivity and shared purpose. When a European astronaut hands a tool to their Russian colleague, there is no moment of hesitation or instruction. The tool is a known quantity. It feels familiar and operates predictably. This seamless interaction reinforces the crew's identity as a single, unified team rather than a collection of national representatives. It removes one more potential barrier, one more source of minor friction, in an environment where crew cohesion is critical to mission success and mental well-being. The lessons learned from this intercultural engineering are already filtering back to Earth, influencing the design of everything from medical devices in international hospitals to consumer products for the global market. The International Space Station, therefore, is more than a laboratory for science. It is a proving ground for a new kind of global design psychology, demonstrating that when we truly design for all of humanity, we create tools that are better, safer, and more intuitive for everyone. Imagine the psychological pressure of knowing that a single failed repair could leave you stranded in orbit, cut off from Earth with dwindling oxygen. Every maintenance procedure in space is shadowed by this immense stakes awareness, a mental burden that tool designers must actively lighten. The instruments used for repairs are therefore engineered not just to fix things, but to fix the mechanic's state of mind, transforming a potential crisis into a series of manageable, confident actions. This begins with the fundamental principle of modularity. Instead of confronting a monolithic, bewildering piece of broken equipment, astronauts work with orbital replacement units, or ORUs. These are essentially modular boxes, each containing a specific function like a computer or a pump. The psychological genius of this system is that it breaks an overwhelming problem into a discrete, solvable task. An astronaut doesn't think the communication system has failed, a thought that could induce panic. Instead, they think, I need to replace the LCU, the loop controller unit. This shift is everything. It channels their focus onto a single, tangible action, replacing a known module with a known spare. This modular approach provides a clear, step-by-step pathway through the problem, offering a powerful sense of progression and control that is essential for mental resilience when the stakes are literally life and death. Once the faulty module is identified, the next psychological hurdle is diagnosis. On Earth, a mechanic might listen for a strange noise or feel for an unusual vibration, senses that are largely unavailable to a suited astronaut. Uncertainty is a relentless source of anxiety. This is where diagnostic tools become psychological lifelines designed to deliver absolute clarity. They are built to provide binary, yes or no answers that strip away any ambiguity. A multimeter won't just give a voltage reading. It will have a large, clear display that flashes green for good and red for bad. A cable tester won't show complex impedance data. It will have a single light that glows to confirm a circuit is complete or remains dark to show a break. This simplification is intentional and profound. It removes the need for interpretation in a high-stress moment, preventing the paralysis of analysis. An astronaut doesn't have to wonder if a reading is borderline or what a slight variation might mean. The tool delivers a verdict, allowing them to move decisively to the next step. This reduction of uncertainty is a direct injection of confidence, replacing nagging doubt with clear direction. The repair process itself is where tool design most directly interfaces with the astronaut's cognitive load. Remembering a complex 20-step procedure from a manual while floating in microgravity is not just difficult, it's a dangerous distraction. The solution is to physically embed the instructions into the tools and the workspace. The tools designed for module replacement are often themselves modular, with attachments that only fit the correct fittings, making it impossible to proceed incorrectly. But the true psychological masterstroke is the use of guided procedures. The pistol grip tool, for instance, can be pre-programmed with a specific torque sequence for a particular task. The astronaut simply follows prompts on the tool's display, turning bolts in the order indicated until the tool confirms each step with its satisfying haptic click. The procedure is literally in their hand. Furthermore, work sites are equipped with specialized caddies that hold tools and parts in the exact order they are needed. An astronaut pulls the first tool from the left, uses it, returns it, and then grabs the next one. The physical layout of their workspace becomes a three-dimensional checklist, eliminating the cognitive burden of memory and ensuring not a single step is missed. This system externalizes the procedure, allowing the astronaut to offload the mental checklist and focus entirely on the quality of each individual action. The cumulative psychological effect of these design choices is transformative. A situation that should be terrifying, performing delicate surgery on a machine that keeps you alive in the void of space, is reframed as a familiar, almost routine series of steps. The tools themselves become partners in the repair, actively guiding the astronaut, confirming their progress and preventing errors. This builds a deep, earned confidence that is the absolute bedrock of mental resilience on long-duration missions. Astronauts have reported that this structured, tool-guided approach creates a sense of calm focus, where anxiety is replaced by a state of flow. They know the tools have been designed by teams of brilliant engineers who have anticipated every possible problem and designed a solution for it. This trust in the equipment translates into trust in themselves and their ability to handle whatever the mission throws at them. The repair is no longer a potential catastrophe. It's just another job they are magnificently equipped to handle. So how do engineers move beyond brilliant intuition and into the realm of predictable scientific success? The answer lies in a rigorous formal discipline known as human factors engineering, a field that treats the interaction between a human and a tool as a complex system to be optimized with empirical data. This is the science that transformed space tool design from an art form into a predictive science, ensuring that every curve, button, and texture isn't just a designer's best guess, but a data-driven decision aimed at maximizing both performance and psychological comfort. The laboratory for this work is often as extraordinary as the tools themselves. Before a single piece of metal is ever cut, prototypes undergo exhaustive usability testing in environments that simulate the disorienting conditions of space. NASA makes extensive use of its neutral buoyancy laboratory, a gigantic swimming pool where astronauts, weighted to be neither sink nor float, practice tasks with tool prototypes while fully suited. But the testing goes far beyond simply seeing if a task can be completed. Researchers closely observe the astronauts' body language, their movements, and their pace. How many times do they fumble with the tool? How often do they have to stop and reorient it? Do they show signs of frustration or fatigue? This observational data is priceless, revealing ergonomic flaws and cognitive confusions that would never appear in a theoretical model. It's here that a handle diameter might be increased by a few millimeters, or a button might be relocated to a more intuitive position, all based on the unconscious struggles of a test subject trying to work effectively while simulating weightlessness. The analysis goes even deeper with the use of sophisticated eye-tracking technology. Test subjects wear specialized goggles that precisely monitor where their gaze is focused and for how long. This reveals the visual journey an astronaut takes when using a tool. Are their eyes constantly darting between the workpiece and a tiny readout on the tool itself, creating a taxing cognitive load? This data might lead designers to integrate a larger, more central display. Or perhaps the eye tracking shows that an astronaut consistently misses a critical warning light because it's placed outside their natural field of view while performing a task. This objective measure of visual attention allows engineers to redesign the tool's interface, placing the most vital information exactly where the user's eyes naturally want to look, creating a seamless and effortless flow of information that drastically reduces mental strain. Perhaps the most revealing data comes from biometric monitoring. Astronauts testing prototype tools are wired with sensors that track heart rate, skin conductance, and even brainwave patterns. This provides an unfiltered, objective window into their psychological state that goes far beyond what they can self-report. A designer might see a subtle but consistent spike in heart rate every time an astronaut uses a particular latch mechanism. This physiological stress response, perhaps undetectable to the user themselves, indicates a subconscious anxiety or lack of confidence in that part of the tool's operation. Conversely, a steady, calm biometric readout during a complex procedure confirms that the tool's design is supporting a state of focused flow rather than inducing panic. This biometric feedback loop is crucial for validating designs, proving that a tool doesn't just work in a mechanical sense, but that it genuinely supports the mental well-being of the operator under duress. All of this rigorous experimentation is centralized within organizations like NAS, a human factors division, where teams of scientists have built vast databases of anthropometric and psychological data. They have conducted thousands of experiments to determine the exact optimal diameter for a tool handle used by a suited astronaut, a measurement that balances secure grip against hand fatigue. They have precise specifications for the amount of force required to activate a button or toggle a switch, enough to prevent accidental activation, but not so much that it becomes a taxing effort. The spacing between controls is meticulously calculated to prevent a gloved finger from pressing two buttons at once. Every single one of these minutiae is backed by hard science, replacing tradition and guesswork with empirical evidence. This scientific, human-centered approach ensures that the final product is more than just a well-made instrument. It is a psychologically attuned partner, designed from the atoms up to keep its human operator calm, confident, and in complete control amidst the infinite uncertainties of space. Despite the mountains of data from simulations and lab testing, there is one irreplaceable source of truth in the quest for perfect tool design: the astronauts who have actually used them in orbit. These individuals are far more than just operators. They are the crucial final link in an ongoing engineering feedback loop, their lived experience providing the raw material for the next generation of improvements. The design process doesn't end when a tool is launched. In many ways, that's when the most valuable phase begins. Through an intricate system of post-mission debriefings, in-flight notes, and meticulous video analysis, every comment, every hesitation, and every moment of frustration is captured and fed back to the designers on Earth, transforming anecdotal experience into hard engineering data. This feedback is gathered with an almost clinical level of detail. After a spacewalk, astronauts will spend hours in structured debriefing sessions with human factors engineers and tool designers. These aren't casual conversations. They are methodical interviews designed to extract every nuance of the experience. An engineer might play back video footage of a specific repair task and ask the astronaut to narrate their thought process moment by moment. What were you feeling here when you reached for the connector? Did the tool feel balanced in your hand when you were in that inverted position? Tell me about the sound it made when it engaged. Was that click distinct enough over the sound of your own breathing in the helmet? This forensic analysis reveals problems that would never show up in a lab. A tool might meet all its technical specifications yet still cause a low-level, subconscious anxiety because its center of gravity feels slightly off when used in a particular orientation, making the astronaut feel like they're fighting to control it. One of the most famous examples of this feedback-driven redesign involves the handles on many of the tools used for external maintenance on the International Space Station. The original handles were perfectly cylindrical, a shape that is efficient to manufacture and looks clean on a blueprint. But astronauts returning from early missions reported an unexpected issue. In the bulky pressurized gloves, a smooth, cylindrical handle had a tendency to rotate slightly during precise operations. This required the astronaut to constantly micro-adjust their grip, a small but continuous drain on their concentration and a source of minor stress. The solution, directly born from this feedback, was to redesign the handles with a subtle but critical hexagonal or octagonal cross-section. These flat facets gave the glove something to bite against, preventing that tiny, annoying rotation. The change was minimal from a manufacturing standpoint, but its psychological impact was enormous. It eliminated a persistent, low-grade irritation, allowing the astronaut to focus entirely on the task instead of their grip. The feedback loop also uncovers more complex psychological mismatches. Astronauts reported that some auditory feedback signals, designed to be reassuring, were actually causing confusion during high-stress moments. A tool might have been programmed to emit a high-pitched beep to signal the start of a mode and a low-pitched beep to signal the end. Under the calm conditions of training on Earth, this was perfectly clear. But during a complex procedure in orbit, with the astronauts' heart rate elevated and their cognitive load at maximum, those distinct tones could be misheard or misinterpreted. The stress of the environment changed the perception of the sound. Based on this feedback, designers moved away from pure tonal beeps and towards more distinct, complex sound signatures. A short sequence of chirps for one function, a longer warble for another. These unique auditory patterns were far more easily distinguished by a brain under pressure, turning a potential source of error back into a reliable confirmation. This process ensures that tool evolution is never driven solely by theoretical assumptions or the whims of an engineer in a lab. It is grounded in the messy, unpredictable, and profoundly human reality of spaceflight. Each mission, each spacewalk, each repair becomes a live fire test that provides invaluable data to refine and perfect the interface between human and machine. The astronauts, in sharing their frustrations and their successes, become active co-designers. Their cumulative experience is literally sculpted into the next iteration of the tools they use, creating an ever-tightening bond of trust. They know that their feedback matters, that their discomfort will be addressed, and that the tools they use tomorrow will be better than the ones they use today. This collaborative cycle is what transforms a good tool into a great one, and a great tool into a trusted companion on the most dangerous journey a human can undertake. This shift to virtual prototyping represents a quantum leap in how we understand the human element of tool design. Before a single gram of titanium is ever milled or a single polymer grip is molded, engineers can now immerse astronauts in a completely digital workshop, observing not just what they do, but how they feel while they're doing it. The virtual environment is a psychological playground, a safe space to fail spectacularly. A designer can watch as an astronaut, represented by a motion-captured avatar, instinctively reaches for a control that isn't there on a virtual tool model, revealing an unconscious expectation that a flat blueprint could never show. They can introduce deliberate, frustrating flaws into the simulation, a switch that's slightly too stiff, a display that's hard to read from an awkward angle, and measure the resulting dip in efficiency and rise in stress. This ability to test 100 different iterations of a handle shape or button layout in the time it used to take to machine one physical prototype has completely transformed the design timeline, compressing years of trial and error into months of targeted, data-rich experimentation. The magic of this process lies in its ability to simulate the most crucial sense for tool interaction, touch. Advanced haptic feedback systems are the key. An astronaut wearing a VR headset and haptic gloves isn't just seeing a virtual wrench, they're feeling it. Sophisticated actuators in the gloves generate precise resistance patterns, simulating the weight and balance of the digital tool. When the virtual wrench makes contact with a virtual bolt, the gloves can deliver a sharp, convincing jolt to simulate the moment of engagement. This allows designers to test the psychological impact of different feedback mechanisms. Does a high-frequency vibration signal success more clearly than a single, solid thump? Does a tool that feels slightly heavier in the virtual hand inspire more confidence than a feather-light one, even if its actual mass would be identical? This data is priceless. It moves design choices beyond guesswork about what should feel right into the realm of knowing what actually does feel right to the person who will bet their life on it, all before a single physical part exists. Even more revealing than the conscious actions is the unconscious data, the information our bodies give off without us even knowing. This is where eye-tracking technology within the VR headset becomes a window into the astronaut's soul. Where does their gaze linger when they first pick up a new virtual tool? Are they immediately drawn to the correct control, or do their eyes dart around in confusion, searching for a switch that isn't intuitively placed? This visual hesitation, measured in milliseconds, is a huge red flag for designers. It reveals a cognitive disconnect, a moment of friction that could become a critical error under the stress of a real spacewalk. Conversely, a tool design that immediately focuses the user's gaze on the most important element receives a high psychological score. This eye-tracking data allows engineers to refine the visual hierarchy of a tool, using color, shape, and contrast to naturally guide the eye to the right place at the right time, creating an interface that feels effortless and intuitive. The most objective measure of all comes from the astronaut's own physiology. During these VR sessions, test subjects are wired with a suite of biometric sensors that monitor heart rate, skin conductance, and even brainwave patterns. This turns subjective feelings into hard, quantifiable data. A designer can see a clear spike in heart rate and skin sweatiness every time an astronaut uses a particular latch mechanism. This physiological stress response, which the astronaut might not even verbally report, tells the engineers that aspect of the design is causing subconscious anxiety or frustration. It's failing the psychological test. On the flip side, a calm, steady biometric readout during a complex virtual procedure is the ultimate stamp of approval. It proves the tool's design is supporting a state of focused flow, not inducing panic. This fusion of virtual reality, haptic feedback, and biometrics has created the most powerful human factors testing laboratory ever conceived. One where the psychological optimization of a tool is given the same rigorous scientific attention as its tensile strength or thermal properties. This deliberate application of color psychology extends far beyond simple decoration. It creates a silent, efficient communication system that speaks directly to the astronaut's subconscious. In the visually chaotic environment of a space station, where every surface is covered with cables, panels, and equipment, a brightly colored tool handle acts like a visual beacon. A frequently used device like a precision torque driver for daily maintenance might be given a calming shade of blue. This color is not chosen at random. Psychologically, blue is associated with stability, trust, and focus. For an astronaut performing a repetitive but critical task, that subtle visual cue can have a grounding effect, promoting a state of calm concentration amidst a backdrop of potential distractions. It signals a routine operation, allowing the mind to settle into a familiar, manageable rhythm. Conversely, the most urgent and critical tools are almost universally marked with high visibility red or orange. An emergency hatch release, a fire extinguisher, or a critical medical kit isn't just labeled in red. Its entire housing might be painted in a vibrant, warning shade. This leverages a deep-seated, almost primal psychological response. Red signals danger, urgency, and the need for immediate action across nearly all cultures. In a crisis scenario where every second counts and cognitive function is narrowed by stress, that flash of red cuts through the noise. It allows an astronaut to bypass any conscious thought process and react instinctively, their hand already moving toward the tool before their brain has fully processed the words on its label. This instant recognition is a powerful cognitive shortcut, shaving off precious seconds that could mean the difference between containment and catastrophe. Perhaps even more clever is the strategic use of neutral, subdued colors for tools that need to fade into the background. During incredibly delicate operations like repairing a sensitive circuit board or manipulating a fragile scientific sample, visual distractions are more than just annoying, they can be disastrous. A tool with a shiny, reflective surface or a brightly colored handle could catch the light and create a glare, or its color could draw the eye away from the ultra-precise work at hand. For these instruments, designers select matte finishes in shades of gray, charcoal, or flat black. These tools are psychologically designed to be unobtrusive. They don't demand visual attention, they facilitate it, keeping the astronaut's focus laser locked on the task itself. This careful management of the visual field is a subtle yet profound way to support peak performance during operations that require absolute precision. This visual language is further refined through an intense focus on contrast and visibility. The lighting inside a spacecraft is not like the steady, full-spectrum light of the sun on Earth. It can be a patchwork of shadows from equipment, the harsh, direct light from headlamps, and the cool glow of LED panels. A color that looks perfectly clear under one light might become difficult to distinguish under another. Designers meticulously test color combinations for their contrast ratios under these exact lighting conditions. A yellow stripe on a white handle would offer poor contrast and could be easily missed. Instead, you'll see high-contrast pairings like black on yellow or white on navy blue. This ensures that markings and symbols remain starkly visible and instantly legible from any angle and under any lighting scenario, preventing a simple misidentification from snowballing into a major error. Finally, this entire system is made universal through the use of internationally recognized symbols. While English is the common language on the International Space Station, relying on text alone would introduce a critical point of failure, requiring translation and precious extra milliseconds to read. Instead, tools use a vocabulary of symbols, a universal visual language. A lightning bolt denotes electrical hazard. A flame indicates a fire-related function. An arrow shows the direction of force or rotation. These symbols are tested across cultures to ensure they are intuitively understood by astronauts from the United States, Russia, Japan, and all partner nations. This removes the cognitive load of language processing, allowing for immediate comprehension. Together, this sophisticated interplay of color psychology, contrast optimization, and symbolic communication forms a silent, seamless support system. It offloads a significant amount of mental work from the astronaut, allowing them to operate not just with their hands, but with a visual environment that is actively working to keep them calm, focused, and error-free. The logical next step in this incredible journey of human-centered design is a shift from tools that understand the human condition to tools that can actually perceive it in real time, responding not just to the task, but to the very state of the person holding them. We are entering an era where the line between tool and partner will blur completely, with the emergence of AI adaptive instruments that act as responsive extensions of the astronaut's own nervous system. Imagine a drill that senses the subtle tremor of anxiety in your hand and activates internal gyroscopes to stabilize itself, or a diagnostic device that recognizes your cognitive overload and simplifies its complex display into a single, glaringly obvious instruction. This is no longer science fiction. It is the bleeding edge of space tool design, where technology begins to empathize. The foundation of this revolution is biometric sensing, woven seamlessly into the very fabric of the tool. Future prototypes will be embedded with a network of microscopic sensors capable of reading a suite of physiological data points through the astronaut's glove. These sensors won't just measure grip pressure, they will detect the minute micro vibrations of muscle fatigue long before the astronaut becomes consciously aware of their own exhaustion. They will monitor galvanic skin response, the subtle electrical changes that indicate rising stress levels and heart rate variability, a key indicator of cognitive load and emotional state. The tool itself becomes a diagnostic device, not for the machine it is repairing, but for the human operating it, creating a continuous, real-time feedback loop of the user's psychological and physiological condition. This constant stream of biodata will be processed by onboard artificial intelligence, algorithms trained to recognize specific patterns that correlate with performance degradation. The true genius of these systems will be their proactive response. Consider a scenario where an astronaut is performing a high-precision soldering task on a circuit board outside the station. The AI, monitoring a slight increase in hand tremor and a quickening pulse, interprets this as the onset of task-induced stress. Before the astronaut's unsteady hand can jeopardize the connection, the tool could automatically engage a micro-adjustment system. Tiny piezoelectric actuators within the handle might make imperceptible counter-movements, neutralizing the shake and keeping the tip perfectly steady. The tool effectively becomes a smart, active filter for human error, compensating for the physiological impacts of stress to ensure a perfect outcome every single time. The adaptation will extend beyond physical stabilization into the very way information is presented. Cognitive overload is a silent threat during complex procedures, where an astronaut might be juggling verbal instructions from mission control, data from multiple instruments, and the physical task itself. An AI adaptive tool could detect the signs of this overload, perhaps through a specific pattern of rapid eye movements caught by a tiny embedded camera or a change in the user's grip pattern. In response, the tool could dynamically simplify its own user interface. A screen cluttered with 10 data points might instantly shrink down to show only the 2 most critical numbers, highlighted in bold. Alternatively, it could switch from visual to auditory cues, providing a calm, spoken-word prompt to guide the next action, effectively offloading processing from the overwhelmed visual cortex to the auditory system. Perhaps the most profoundly human aspect of this technology will be its capacity for encouragement. Long-duration spaceflight is as much a psychological marathon as a physical one, marked by periods of intense frustration and isolation. Future tools might be designed to offer subtle haptic encouragement. If the system's sensors detect the physiological signatures of frustration, a clenched grip, a surge in skin conductance, the tool could respond with a unique vibration pattern. Not an alarm, but a deliberate, calming pulse, a kind of digital pat on the shoulder that says, "I'm here, you've got this." This empathetic response transforms the tool from a cold piece of hardware into a supportive teammate, capable of boosting morale and resilience at the very moment it's needed most. This represents the ultimate synthesis of engineering and psychology, creating a partnership where human and machine are inextricably linked in a shared loop of action, perception, and adaptive response. These extraordinary innovations, born from the necessity of keeping astronauts alive and focused in orbit, have not remained locked away in the space program. Instead, they have undergone a remarkable process of psychological spillover, where the core principles developed for the most extreme human experiences have been translated and adapted to revolutionize the tools we use here on Earth every single day. This cross-pollination of ideas proves a powerful truth. When you design for the absolute limits of human performance, you uncover universal insights that benefit everyone, bringing a little bit of space-age thoughtfulness and psychological support into our daily routines. One of the most significant transfers of knowledge is in the field of medicine, particularly in the design of modern surgical instruments. Just like an astronaut on a spacewalk, a surgeon in an operating theater operates under immense cognitive load and time pressure, where a moment of confusion or a fumbled instrument can have dire consequences. The principles of cognitive load reduction perfected for space tools have become absolutely central to surgical design. You can see it in the color coding of instruments in an operating tray, where a flash of blue might indicate a clamp and a band of green identifies a specific scissor, allowing a nurse to hand the correct tool to the surgeon without a word being exchanged, their eyes never leaving the operative field. This visual shorthand drastically reduces the mental effort required for communication during a complex procedure. Furthermore, the ergonomic handles on laparoscopic tools are a direct descendant of space glove design. They are meticulously contoured to fit the hand perfectly, reducing muscle fatigue during hours-long procedures and providing clear tactile landmarks so the surgeon always knows the orientation of the tool's tip inside the patient's body, even when they can't see it directly. This seamless integration of form and function, designed to keep the user's mind completely focused on the task, is a pure transfer of astronaut-grade psychological engineering into the operating room, saving lives right here on the ground. The haptic feedback systems engineered to give astronauts a simulated sense of touch and weight in the void have also found a vibrant and unexpected second life in the palms of billions of people through their smartphones and game controllers. That gentle, satisfying vibration you feel when you type on a touchscreen keyboard or when your character in a video game fires a weapon is not a simple motor. It is a sophisticated language of touch, a direct descendant of the systems designed to communicate with astronauts through their pressurized gloves. Modern devices use precise, programmable vibration patterns known as haptics to provide confirmation and create a more immersive, intuitive experience. Your phone doesn't just silently register a button press, it vibrates softly to tell your brain, input received. This tiny, artificial sensation replaces the physical feedback missing from a flat glass screen, reducing the cognitive uncertainty of whether you actually hit the right key. In video game controllers, advanced haptic systems can simulate everything from the light patter of rain to the jarring recoil of a shotgun, translating on-screen events into a rich tactile language. This technology transforms our interaction with digital worlds from a purely visual and auditory experience into a multisensory one, making it feel more real and responsive. This entire field of consumer haptics owes a significant debt to the psychologists and engineers who first had to solve the problem of how to make a weightless tool feel trustworthy and communicative to a human floating in the silent darkness of space. Perhaps the most vital spillover effect is found in the design of industrial safety equipment, where the error prevention principles of spaceflight are applied to prevent workplace accidents. The concept of mistake-proofing, or poker yoke, as it's known in manufacturing, has been supercharged by the space program's absolute insistence on designing out the very possibility of human error. You can see it in the asymmetrical connectors used in heavy machinery, designed so that hydraulic lines can only be attached in the correct configuration. It is physically impossible to hook them up backward, preventing catastrophic failures that could injure workers or damage equipment. This is the exact same philosophy used on the International Space Station's fluid quick disconnects. Similarly, safety interlocks on factory equipment ensure that a guard must be fully and securely in place before a powerful press or cutter can be activated. The machine will not function unless the safe procedure is followed, just like the tools designed for Hubble that would not release a component until all the preparatory steps were verified. These designs remove the burden of constant, perfect vigilance from the human operator. They acknowledge that people get tired, distracted, and rushed, and they build a system of physical safeguards that enforces safe behavior. This proactive approach to safety, which creates an environment where it's easier to do the right thing than the wrong thing, is a powerful psychological gift from the world of space exploration, one that has undoubtedly prevented countless injuries and saved innumerable lives in factories, workshops, and construction sites around the globe. Despite the meticulous engineering and rigorous testing that goes into every piece of space hardware, the history of astronaut-tool design is not an unbroken string of successes. Some of the most valuable lessons have been learned not from what worked perfectly, but from designs that failed the human being using them, creating psychological stress, confusion, or even fear despite meeting every technical specification on paper. These failures are not marks of shame. They are crucial data points that highlight the profound complexity of the human-machine relationship in an environment where there is no room for error. One of the most telling examples comes from the early days of the Space Shuttle program, with a tool designed for a specific, high-stakes rendezvous procedure. The device was technically flawless, a marvel of precision machining that performed its mechanical function without a hitch. But its user interface was a dense cluster of nearly identical toggle switches and unlabeled indicators. During ground simulations, highly trained astronauts could operate it without issue. However, during an actual mission, with the stress of a real orbital rendezvous and the ever-present knowledge that a mistake could mean a catastrophic collision, that same interface became cognitively overwhelming. The mental effort required to decipher the correct sequence under pressure created a palpable anxiety, a feeling that the tool was fighting them rather than helping them. The design was subsequently overhauled, not to change its function, but to radically simplify its interface with large, color-coded, and distinctly shaped controls that could be operated without conscious thought, proving that a tool's true performance is measured not in a vacuum chamber but in the mind of the stressed operator. Ambiguous feedback mechanisms have also been a significant source of psychological strain. There is a famous case of a powered cutting tool developed for a satellite repair mission. The tool was designed to sever a thick metal strap with a precise, guillotine-like action. Technically, it was a masterpiece, but its feedback system relied on a single, subtle tone that sounded at the moment the cut was complete. During testing in the noisy, echoing environment of a spacecraft, astronauts repeatedly reported uncertainty. Was that faint chime the confirmation sound, or just a random noise from the life support system? That moment of doubt, that split second of questioning whether a life-critical task had actually been completed, was psychologically torturous. It forced the astronaut to visually verify the cut, a difficult maneuver in itself, breaking their concentration and flow. The solution was not to make the sound louder, but to change the nature of the feedback entirely. Engineers replaced the simple tone with a unique, multi-part auditory signature, a distinct sequence of high and low pulses that was impossible to confuse with background noise, coupled with a pronounced haptic shudder through the handle. This multisensory confirmation provided an undeniable signal that cut through both the acoustic and psychological noise, restoring the astronauts' confidence and allowing them to trust the tool implicitly. Sometimes the psychological failure is more subtle, manifesting as an inexplicable aversion or superstition that develops among crew members. A specific torque wrench used on one long-duration space station expedition earned an unofficial and unfortunate nickname among the crew due to its peculiar handling characteristics. While it met its torque accuracy specs, its balance was ever so slightly off-center, requiring a tiny, constant compensatory pressure from the wrist to keep it aligned during use. This minor physical irritation, repeated over hundreds of bolts, created a low-grade but persistent sense of frustration. The tool was not disliked for any single major flaw, but for the cumulative, grating effect of its imperfect ergonomics. It became the tool nobody wanted to use if they could avoid it, with crew members sometimes opting for less efficient methods just to bypass the annoyance. This kind of seemingly irrational aversion is a powerful lesson for designers. A tool's success isn't just about its primary function, but about the entire experience of using it over time. A design that causes even minor subconscious frustration can be rejected by its users, rendering its technical perfection completely irrelevant. Addressing this required going back to the anthropometric data, adjusting the weight distribution by mere grams, and recontouring the handle to eliminate that subtle strain, transforming the wrench from a pariah into a perfectly balanced and trusted member of the toolkit. These case studies collectively underscore a fundamental truth that has become a cornerstone of modern space tool design. A tool is not truly successful unless it supports the psychological state of the astronaut as completely as it performs its mechanical duty. A device that causes anxiety, breeds uncertainty, or creates frustration is a failed device, no matter how well it is machined. The process of fixing these failures almost never involves a major mechanical overhaul. Instead, it demands a deep, empathetic dive into human factors, a willingness to listen to the astronaut's subjective experiences and to treat their reported stress or confusion not as a training issue, but as a critical design flaw. It requires understanding that perception under stress is different from perception in a calm lab, that a sound which is clear in silence can be lost in chaos, and that a minor physical irritation can grow into a major psychological barrier over the long months of a mission. These hard-learned lessons from the dark side of tool design have been instrumental in forging the human-centered philosophy that defines the field today, ensuring that every new instrument is judged not just by what it does, but by how it makes the astronaut feel while doing it. This deep psychological bond between an astronaut and their equipment doesn't magically appear the moment they arrive in orbit. It is meticulously forged over hundreds, sometimes thousands, of hours of grueling, repetitive training here on Earth. The process is a masterclass in building what psychologists call embodied cognition, a state where the knowledge of how to use a tool is stored not just in the brain, but in the very muscles and nerves of the hand, creating an intuition so powerful it can operate flawlessly under the most extreme stress and disorientation. This training begins not with the tools they will use in space, but with tools designed specifically for the unique psychological challenges of learning itself. The foundation is laid in enormous warehouse-sized facilities like NAS, a neutral buoyancy laboratory, a massive swimming pool containing full-scale mock-ups of the International Space Station's modules. Here, astronauts, weighted to be neutrally buoyant, don their pressurized suits and practice every conceivable task they might face. But the goal isn't just to learn the steps, it's to drown out the conscious mind through sheer repetition. An astronaut will practice replacing a failed pump module not just 5 or 10 times, but 50 times. They will do it with their right hand, then their left, then with their body inverted, and then with their vision partially obscured. This relentless, varied repetition is designed to build a robust, flexible muscle memory that is not dependent on any specific body position or perfect conditions. The neural pathways become so deeply engraved that the action of releasing a fastener or mating a connector becomes as automatic and unconscious as breathing. This is the first psychological victory, transforming a complex, high-stakes procedure from a conscious cognitive puzzle into a series of subconscious, fluid motions. Beyond the physical repetition, the training environment is deliberately engineered to induce the psychological pressures of space. The simulations are not calm, quiet exercises. Trainers in mission control introduce realistic malfunctions and unexpected problems mid-task. A communication system might suddenly fail, cutting off the astronaut's link to the Capcom, the capsule communicator. A critical tool might be misplaced in the mock-up, forcing the astronaut to problem solve and adapt on the fly. The water in the pool is kept chilly to simulate the discomfort of the suit, and the sessions are intentionally long and exhausting. All of this is designed to trigger the same stress responses: the elevated heart rate, the narrowed focus, the surge of adrenaline that the astronaut will experience during the real event. The genius of this approach is that it allows them to practice not just the task, but their emotional and psychological response to the task under duress. They learn to recognize the feeling of panic rising and to apply conscious techniques to control their breathing and focus their attention. By the time they reach orbit, the sensation of stress is not a novel, terrifying experience. It is a familiar signal that they have been trained to manage, a known quantity in an otherwise unknown environment. This psychological conditioning is further refined using advanced virtual reality systems that are astonishingly realistic. An astronaut can put on a headset and find themselves floating outside the space station, with the breathtaking but dizzying curvature of the Earth below them. They can reach out with their virtual hand and interact with a perfectly rendered digital model of the pistol grip tool, feeling its weight and texture through haptic feedback gloves. The VR environment allows trainers to create scenarios that would be too dangerous or expensive to simulate physically, like a sudden ammonia leak requiring an emergency shutdown procedure. The psychological power of this training lies in its ability to generate genuine presence, the feeling of actually being in space. The brain, tricked by the immersive visuals and precise physics simulation, begins to form memories and neural associations as if the events were real. This means that when an astronaut finally performs the task for real, their brain doesn't process it as a first-time experience, but as a familiar memory they are simply reliving, drastically reducing the cognitive load and anxiety associated with the unknown. Perhaps the most psychologically astute aspect of the entire process is the design of the training tools themselves. They are not identical to the flight hardware. In many cases, they are heavier, clunkier, and more difficult to use. A training version of a wrench might have a stiffer mechanism or require more force to operate. This is not a design flaw. It is a deliberate feature rooted in a principle sometimes called overtraining. By practicing with a tool that is more difficult to manipulate than the real thing, the astronaut builds greater strength and dexterity. Then, when they switch to the perfectly balanced, exquisitely engineered flight tool, it feels incredibly light, responsive, and easy to control. This creates an immediate and powerful psychological boost of confidence and mastery. The tool doesn't just meet their expectations, it vastly exceeds them, reinforcing the feeling that they are more than capable of handling the job. This careful management of the learning curve, from difficult training tools to sublime flight tools, ensures that the astronaut's final psychological state is one of effortless competence, a quiet certainty that they and their tools are ready for anything the mission can throw at them. For decades, the iconic image of an astronaut was a specific one, and the tools they used were often designed with that single, narrow user in mind. But as space programs around the world have opened their doors to a far more diverse range of individuals, the very definition of the average astronaut has been completely rewritten. This shift has forced a revolutionary and deeply necessary change in design philosophy, moving from creating tools for a hypothetical ideal user to engineering instruments that are truly universal, accommodating the vast spectrum of human physiological and cognitive differences. This isn't just about fairness or inclusivity as abstract concepts. It's a rigorous, practical, and psychological necessity for mission success when your crew's capabilities must be perfectly matched to their equipment. The most immediate and obvious challenge is the sheer physical variation in hand size and strength. A tool handle that feels robust and secure in the large hand of a 6'4" astronaut would be impossibly cumbersome and difficult to control for a smaller crew member. Early space missions often dealt with this by simply providing smaller versions of the same tools, but this was a clumsy and inefficient solution that doubled inventory and created confusion. The modern approach is far more sophisticated, focusing on intelligent, adjustable design. We now see tools with interchangeable palm rests and finger grooves that can be reconfigured in minutes to accommodate different hand geometries. The grip surface itself might be a modular component, allowing an astronaut to swap out a standard grip for one with a more pronounced contour or a softer, more compliant material that provides a secure hold without requiring immense grip strength. This level of personalization does more than improve mechanical efficiency. It sends a powerful psychological message of belonging. It tells every astronaut, regardless of their size, that the tool was designed with them in mind, that their physical presence is not an accommodation but an expectation. This fosters a deep sense of ownership and confidence, eliminating the subtle anxiety of having to make do with equipment that doesn't quite fit. Beyond simple size, designers have had to completely abandon outdated assumptions about physical power and reach. The old paradigm often assumed a certain level of upper body strength to operate stiff levers or to support the weight of a tool for extended periods. This automatically created barriers. The new generation of tools is designed around mechanical advantage and optimal weight distribution, not raw force. Ratcheting mechanisms reduce the range of motion needed to turn a bolt, and geared interfaces multiply the force applied by the astronaut's hand, ensuring that even the most stubborn fastener can be loosened without straining against it. The placement of controls is also critically rethought. Buttons and toggles are positioned based on extensive ergonomic data to fall naturally under the thumb or forefinger of any user, regardless of hand size, eliminating the need for awkward stretching or shifting that can break concentration and increase fatigue. This thoughtful engineering ensures that physical tasks are limited by the tool's capability, not the astronauts, creating a more level playing field where success is determined by skill and knowledge, not by brute strength. Perhaps the most nuanced advancement is in acknowledging and designing for different cognitive processing styles. The way individuals perceive information, prioritize tasks, and solve problems can vary significantly. A tool interface that presents a dense array of data in a single format might be perfectly intuitive for one astronaut while being overwhelmingly confusing for another. The solution lies in building flexibility and redundancy into the way tools communicate. The pistol grip tool, for instance, doesn't rely on a single mode of feedback. It provides information visually through its digital display, audibly through distinct tones, and tactilely through haptic vibrations in the handle. This multi-sensory approach allows astronauts to gravitate toward the feedback channel they find most intuitive and reliable under stress. One might primarily watch the torque readout on the screen, while another might close their eyes for a second to focus on the confirming click felt through their glove. By providing the same critical information through multiple pathways, the tool respects different cognitive preferences, reducing the mental effort required to interpret its signals and preventing potentially dangerous misunderstandings. This commitment to universal design is rigorously validated through testing protocols that are intentionally inclusive. Prototype tools are not just evaluated by veteran astronauts with years of experience. they are put into the hands of a diverse pool of test subjects that reflects the actual composition of modern astronaut corps. Engineers closely observe how people with different anthropometrics, strength levels, and cognitive styles interact with the equipment. They look for patterns. Does a particular latch mechanism consistently cause difficulty for people with smaller hands? Does a certain alert sound get misinterpreted more frequently by some test subjects? This data is not used to weed people out, but to refine the design until those points of friction are eliminated for everyone. The goal is a tool that feels like a natural, effortless extension of the body and mind for the entire human spectrum, from the 5th percentile female to the 95th percentile male and every variation in between. This process inherently leads to better, more robust designs for all users. A handle that is easier for a smaller hand to grip will also reduce fatigue for a larger hand over a long task. An interface that is clear and unambiguous for a novice will also prevent errors by an expert working under duress. By designing for the edges of human experience, we inevitably improve the experience for the center, creating tools that are not only more inclusive but also more intelligent, resilient, and effective for every single person who relies on them. Every ounce of cargo launched into orbit carries an immense cost, not just in dollars but in the precious and limited volume of a spacecraft. This brutal calculus of weight and Space Force's mission planners into a constant tug of war between two competing ideals: the pure psychological efficiency of a specialized tool designed for one perfect task, and the practical necessity of a multi-function device that can perform a dozen jobs in a single, compact package. This is far more than an engineering debate. It is a deep exploration of how the human mind prefers to interact with technology, especially under the extreme pressures of spaceflight. A specialist tool, like a custom-designed torque wrench for a specific panel bolt, offers an almost subconscious ease of use. Its form screams its function. There are no buttons to select, no modes to toggle, no risk of using the wrong setting. Picking it up, the astronaut's brain can immediately switch into autopilot, the muscle memory for that one specific action taking over completely. This cognitive economy is a form of psychological comfort food, familiar, reliable, and requiring zero mental effort to digest. In a high-stress moment, that simplicity is priceless. Yet, the manifest doesn't lie. You cannot afford to carry 50 individual specialist tools for 50 individual tasks. The solution is the multi-function tool, a masterpiece of miniaturization and integrated design. But this practical marvel introduces a new and potentially dangerous variable: cognitive load. Every additional function baked into a single device is another layer of complexity the astronaut must manage. A simple screwdriver is just a screwdriver, but a multi-function tool might be a screwdriver, a wrench, a cutter, and a pry bar, all controlled by a series of latches, switches, and collars. The user must now engage their conscious brain to answer a series of questions before they can even begin the task. What mode is it in? How do I switch it to the function I need? Is it configured correctly? This moment of hesitation and mental menu navigation is the enemy of flow state. In the demanding environment of space, where time and focus are critical resources, a poorly designed multi-function tool can become a cognitive tax machine, draining attention away from the larger, more important procedure at hand. The legendary NASA-approved pocket knife, often based on commercial designs from companies like Victorinox, is a fascinating case study in mitigating this cognitive tax. While it boasts over 20 separate functions, its designers employed brilliant psychological tricks to keep it intuitive. The most important is the principle of physical affordance. The tool doesn't hide its functions behind a digital menu. Each one has a dedicated physical actuator. The large cutout for your thumbnail on the screwdriver blade naturally invites you to pull it out. The distinct, serrated texture of the saw blade feels different from the smooth spine of the main blade. These tactile and visual cues allow an astronaut to select the right tool by feel and pattern recognition, minimizing the need for conscious thought. You don't have to think about how to open the scissors. Your thumb finds the familiar notch and pulls. This design leverages existing, deeply ingrained mental models from everyday life, allowing the complex tool to feel surprisingly simple and familiar in the hand. Furthermore, the layout is a lesson in logical grouping and error prevention. Functions are often arranged so that you cannot accidentally deploy two tools at once that might interfere with each other or pose a safety hazard. The process of opening one blade often locks others in place, a physical interlock that prevents the user from making a dangerous mistake. This built-in safety net provides a subtle psychological reassurance, allowing the astronaut to use the tool with confidence rather than trepidation. The designers also understand the power of spatial memory. After even a short period of use, your hand learns exactly where each tool is located on the chassis. Deploying the bottle opener becomes a quick, fidget-like motion, not a conscious search. This transforms the tool from a collection of 20 separate items into a single, familiar object whose complexity has been effectively offloaded from the user's working memory and into their muscle memory. The ultimate psychological challenge, however, lies in convincing veteran astronauts to trust these multi-function wonders over their beloved specialists. An astronaut who has trained for years with a specific, perfectly balanced torque driver might view a multi-function tool's screwdriver attachment as a flimsy and imprecise compromise. This is where the concept of right tooling becomes paramount. Mission planners are very deliberate about which tasks get a dedicated, specialized tool and which can be reliably handled by a multi-function device. A critical structural bolt that must be torqued to an exact specification with zero margin for error will always get its own single-purpose calibrated wrench. The psychological comfort and guaranteed precision are worth the wait. However, for 100 other smaller tasks, opening a cargo package, cutting a zip tie, adjusting a wire, the multi-function tool is not just adequate, it is ideal. This careful curation builds trust. When an astronaut sees that the multi-function tool is only deployed for jobs within its capabilities, and that the specialists are always used for the most critical applications, their psychological resistance begins to fade. The multi-function tool earns its place not as a replacement, but as an indispensable partner, handling the routine so the specialists can focus on the extraordinary. This delicate balance between the comfort of specialization and the necessity of versatility reveals a profound truth about tool design. The most advanced technology in the world is useless if it fails to earn the trust and intuitive understanding of the human being who holds it. Floating in the confined, module-packed environment of a spacecraft, an astronaut's world is a carefully managed equilibrium of order and chaos. Every object must have its designated place, not just for physical safety, but for psychological sanity. This brings us to a dimension of tool design that is often overlooked yet utterly critical: the psychology of storage. In microgravity, a tool left out doesn't just sit on a table. It becomes a drifting hazard, a visual pollutant, and a constant, nagging reminder of disorder. How and where these vital instruments are kept when not in use is not a mere logistical afterthought. It is a fundamental part of the psychological support system that enables astronauts to function at their peak in an inherently disorienting environment. The primary psychological benefit of a well-designed storage system is a drastic reduction in cognitive load. Imagine the mental toll of trying to locate a specific socket adapter in a jumbled bag of identical-looking metal pieces, all while floating in a space where there is no natural, up to orient the bag itself. A moment of frustrated searching is a moment of wasted oxygen, mission time, and, most importantly, precious mental focus. This is why tool storage in space is engineered for instant visual and tactile recognition. Tools are not tossed into a generic pouch. They are housed in custom-fitted caddies, often made of semi-transparent material, with each instrument held securely in its own contoured nest by elastic bands or soft clamps. The layout of these caddies is not random. It is a direct reflection of the procedural steps for a given task. The first tool needed is on the left, the next is to its right, and so on. This transforms the storage system into a three-dimensional checklist. An astronaut's hand can move through the caddy in a smooth, practiced sequence, grabbing each tool without their eyes ever needing to leave the workpiece. This externalization of procedure is a powerful cognitive offload. It means the astronaut doesn't have to waste mental energy remembering what comes next or hunting for the right piece of equipment. The storage system itself guides the action, preserving their cognitive resources for the complex problem-solving required by the task itself. Beyond mere organization, the method of securement is itself a psychological anchor. The constant, subtle anxiety of a tool drifting away is eliminated by storage solutions that provide unambiguous physical confirmation. Magnetic toolboards are a perfect example. A tool equipped with a ferrous plate doesn't just stick to the board. It snaps into place with a satisfying solidity that can be felt through an astronaut's glove. This positive engagement is a tiny but important psychological reward. It signals that the tool is safe, secure, and exactly where it belongs. Similarly, tools stored in drawers are not simply placed inside. They are locked down with positive latching mechanisms that give both a tactile and an auditory click when properly secured. These deliberate feedback mechanisms do more than prevent accidents. They build a rhythm of order and control. Every time a tool is returned to its designated spot with a confirming snap or click, it reinforces the astronaut's sense of command over their environment. In a world where so many forces are beyond their control, this mastery of their immediate workspace is a vital source of confidence and psychological stability. The impact extends to the very aesthetics of the living and working space. A spacecraft interior is a dense jungle of wires, panels, and equipment. Visual clutter is not just an eyesore, it is a genuine source of stress that can contribute to cognitive overload and fatigue. A toolkit left in disarray, with tools floating at odd angles and tetners crisscrossing, adds to this visual noise, creating a subconscious sense of chaos. A well-designed storage system, by contrast, creates visual cleanliness. When all tools are stowed, the caddy presents a smooth, uniform, and predictable surface. Tethers are neatly coiled and clipped. The workspace appears calm and controlled. This visual order has a profound calming effect on the human psyche. It tells the astronaut that their environment is under control, that everything is in its place, and that they can focus on their work without the background anxiety of looming disorder. This is why astronauts are rigorously trained in what NASA calls good housekeeping. It is not about being tidy for its own sake. It is a recognized psychological protocol for maintaining mental well-being and operational efficiency in an environment where there is no room for error. The predictable, ordered landscape of a properly stowed tool kit is a small oasis of Earth-like normality in the alien world of space, a silent promise that even here, amidst the infinite unknown, there is a place for everything and everything is in its place. The tools astronauts rely on represent so much more than just mechanical ingenuity or advanced materials. They are, in fact, the physical embodiment of a profound psychological understanding of what it means to be human under the most extreme conditions imaginable. Every curve, every texture, every carefully chosen color is a direct response to the hidden mental and emotional challenges of spaceflight. These instruments are designed to do more than just turn a bolt or cut a wire. They are engineered to reduce cognitive load, to provide emotional comfort through familiar sensations, to build unshakable confidence through flawless performance, and to prevent errors before they can even be conceived. They demonstrate a fundamental truth about technology. It only truly serves humanity when it addresses our mental and emotional needs as completely as our physical requirements. This is human-centered design in its purest, most vital form. And the incredible thing is, these lessons learned in the void are not staying in space. The psychological principles honed over decades of orbital missions are already filtering down, revolutionizing the tools we use here on Earth every single day. The same focus on cognitive load reduction that shaped the pistol grip tool is now seen in the operating room, where color-coded surgical instruments allow a nurse to hand the correct scalpel to a surgeon without a word being exchanged, their eyes never leaving the patient. The haptic feedback technology, first developed to give astronauts a simulated sense of touch and weight, now lives in the palm of your hand, providing the satisfying vibrations in your smartphone that make a touchscreen feel more tangible and responsive. The error prevention designs that made Hubble Space Telescope repairs possible are now built into industrial safety equipment, with asymmetrical connectors and safety interlocks that make it physically impossible to assemble machinery incorrectly, preventing countless workplace accidents. This cross-pollination of ideas proves that when you design for the absolute limits of human performance, you uncover universal insights that benefit everyone, making our world safer, more intuitive, and more responsive to our needs. As we now set our sights on longer, more ambitious journeys to Mars and beyond, the psychological aspects of tool design will only become more critical. A mission to the Red Planet will mean years away from Earth, with crews facing unprecedented levels of isolation and confinement. The tools they use will need to be more than just functional. They will need to be partners in maintaining mental well-being. We can expect to see the next generation of AI adaptive instruments that monitor an astronaut's stress levels and adjust their interface accordingly, or tools with built-in biometric sensors that can warn of fatigue before the user even recognizes it themselves. The goal will be to create a seamless, almost symbiotic relationship between human and instrument, ensuring that as we reach further into the cosmos, we don't leave our humanity behind. Instead, we bring the very best of human-centered design with us, using deep psychological insight to craft technology that supports, empowers, and understands us. So the next time you pick up a well-designed tool, a chef's knife that feels perfectly balanced in your hand, a drill whose grip seems to mold to your fingers, or a car whose controls are exactly where you expect them to be, take a moment to appreciate its elegance. That sense of effortless intuition, that feeling of a natural extension of your own will, may very well owe a silent debt to the countless engineers and psychologists who first had to solve these problems not for a workshop on Earth, but for the ultimate human adventure, the exploration of space. If this journey into the psychology of space tools sparked your curiosity, we'd love to hear from you. Drop a comment below telling us which psychological insight surprised you the most. Was it how color coding reduces cognitive load, or maybe the way haptic feedback creates an artificial sense of weight in the void? Your thoughts help shape what we explore next. To join us for more deep dives into how human factors shape technology, make sure to subscribe and hit that notification bell so you don't miss our upcoming video where we'll delve into the psychology of habitat design in extreme environments. From underwater labs to Mars simulation stations, the way our surroundings influence our minds is another fascinating frontier. And if you have an idea for another extreme environment psychology topic we should cover, let us know in the comments. Your suggestions might just become our next video. Thanks for watching, and we'll see you in the next one.